class, we are now on 3.3 and we're going to be looking at atomic structure. So first, let's start out with understanding an atom. And atoms of each element are unique. I know I've repeated this before. Atoms combine in whole number ratios to form compounds. Atoms are not created nor destroyed in chemical reactions. That means they don't just disappear and things don't get just created out of nowhere. I know in movies, things will just spontaneously appear. That is not possible. Things have to come from something else. So atoms are not created nor destroyed. And this comes from the 1800s. John Dalton had put these atomic theories together. And this is the foundation of where we've built upon how we understand atoms today. So remember, his theories made enormous impact. However, they were not all correct. Atoms can be broken into smaller pieces. Atoms are made up of smaller components, and these are called subatomic particles. So think of cracking open an egg, and now we're going to look at what's inside that egg. So the subatomic particles determine the identity and behavior of atoms. So let's take a look at particles, describing particles. When we look at atoms and subatomic particles, we look at two key things: their mass and their charge. And the mass is an indicate. Well, let me jump back. I'll go into the mass for a minute. But your periodic table, most of them show the mass of that element, excuse me, and the atomic number, which is the protons. When measuring atoms on subatomic particles, we use a unit of mass called atomic mass unit, and it can be represented as a U, and some books will put it as AMU, so I included that as well. These mean the same thing. Atomic mass U. It's abbreviated, so if you see a U or AMU, they mean the same thing. One atomic mass unit is equal to 1.66 times 10 to the negative 27 kilograms. That's a conversion. If we have to do conversion problems, that would be your conversion or equality in order to do the conversion problems. The lightest element is hydrogen and has a mass of 1.0 U, which is equal to 1.66 times 10 to the negative 27 kilograms. So I said there was two things that we look at: their mass and their charge. So if you're looking at a neutral atom, that means that the protons and neutrons equal. It's neutral. It doesn't attract or repel anything. However, we are also looking inside. If they're opposite charge, so when we start looking at charged particles, we look at their interaction with each other. We're going to look at positively charged and negatively charged and no charged particles. Particles with the same charge repel each other. If you ever try to put two magnet ends together, if they're the same side, they will push away no matter how hard you try to put them together. I've never been able to do it. Negative charges do the same. However, opposite charges attract each other. And if you flip one of those magnets, they'll go together. So we're going to look, particles with the same charge, again, repel each other. So that's what you see here, these two here. And understanding these three things here was a big deal because, you know, these are things that we cannot see with our eyes. So to understand this helps explain the behavior of what we're seeing when experiments are done. So this brings us to Volta. In 1800, chemistry pretty much changed. We learned that charged particles affect a form of energy called electricity. And I found a nice little gift so you can see what I'm going to explain. In 1800, Italian scientist Alessandro Volta built the first electrochemical cell, also known as a battery. This contained alternating plates of zinc and copper with pieces of cardboard soaked in sulfuric acid. The two sides were connected by a metal wire. This wire represented an electrical current. This means that there was a flow of charged particles from one side of the battery to the other. Now I found this is an electrochemical cell. We'll eventually cover this, or you'll definitely learn it in 24A. But there's a current that goes from one metal to another metal in a solution that allows these currents to keep happening. So this was a big deal because of electricity. Everything we know in our whole lives revolve around electricity. So separating the elements. So Volta's invention of the battery was a huge milestone in scientists. Scientists used it used it the energy for the so scientists then used the electric energy to separate compounds such as water back into H2O gas. So that's what this figure is representing, is that there's oxygen gas here. What happens is that when the water gets separated into its elements of gas, the gas will push, the water's filled to the top, but the gas is less dense. So it'll push the water down, and even though you can't see it, you can see an empty space where there was none. These spaces are the gas that have pushed down on the water to allow the space for this gas. We at another school, we've done something similar to this, where you can't see the gas, but you can see the space, knowing that the gas was there. Because when you first start, you fill this all the way to the top, so there's no space whatsoever in it. So this battery has separated water into its natural elements, and this is not an easy thing to do. This picture may look like it is. It takes a lot of energy. And if you think about how small a battery is, this is tiny. So yeah, this picture showing this experiment can be reproduced with the modern battery. I don't know how to do it, but I think this is actually really interesting. Okay, so once the idea of a charged particle, once charged particles were identified, they excuse me, they wanted to know how they interact with each other. So to learn, one way was to connect a battery of two plates. And the particles, one plate was positively charged, so you see here the plus signs, and one was negatively charged. And particles were injected in between the plates. And so this is a particle source, so it's coming out from here, and it's going to the target, which is over here. The particles curved towards the oppositely charged plates, so it was attracted to what was the opposite charge of it. This behavior allows scientists to determine the charges on different particles. So because this is a negative, it's going to repel and stay away from this as much as possible, be attracted to the positive. So this curve, it actually, I think this should actually kind of go down here, and you can kind of see it curve more where it goes like this, if you can visualize what my mouse is doing. So this was able to tell us about how, what kind of particles were we dealing with? Were we dealing with a negative, a neutral, or a positive? Because if it was neutral, it would have stayed in the middle, and if it was oppositely charged, it would have been attracted to the other plate. And J.J. Thomson is the one that, in 1897, J.J. Thomson discovered the electron, which is tiny negatively charged particle that is 2,000 times lighter than the smallest atom. So this was a big deal of understanding what the subatomic particles were and how their behavior affected things. Okay, around the 1900s, scientists knew that atoms contained charged particles, but still did not have enough information regarding how they were arranged. So they knew they existed, but they didn't know how they existed inside an atom. Everybody had their own theories, but no one was able to actually prove what was going on. So, Thomson knew that negatively charged particles existed. So there must be positively charged particles to balance the negative ones out. He hypothesized that the small negatively charged electrons were spread out through a positively charged substance that was called the plum pudding model. I have no idea what plum pudding is. It doesn't even sound good to me. But your book kind of describes it as a blueberry muffin. I do like blueberry muffins. I can understand what this is. So this is similar to the plum pudding model. The idea that these electrons were scattered throughout this positively charged substance was his idea of how electrons and protons existed together. This idea did not last long, though. So then comes Ernest Rutherford. And Ernest Rutherford was interested in studying alpha particles. We'll deal with that another time, or you will actually deal with them in another chemistry section. He was interested in seeing the pattern that these particles made when they went through thin gold film. So he surrounded this thin gold film with a material, and this material had some glowing substance on it. So in order to track these alpha particles, he could see the glowing, where it landed, like made an impact on. Think of like putting a tennis ball with powder and then throwing it against the wall. You can see where that would have landed. And through that, he can make a pattern and determine what was going on. So when he did this, he expected the alpha particles to pass completely through the film and hit directly behind it with no problem. So no obstacles, nothing in the way. However, there was something different that happened. He noticed that there was a few particles that reflected and bounced back, and some almost completely deflected 100% back at them. So something was happening. There was hitting a resistance of some sort that was not supposed to be there, and that means that even though most of the alpha particles passed through, there was a few that hit some obstacle with such force that forced them back. Because of this, it led him to believe that the plum pudding model was not correct. So what he came up with is that he believed most of the atom was empty space. So a big volume of empty space with a very dense nucleus at the center. And because of this empty space, that's how most of the alpha particles were able to pass through, because it was just empty volume and the alpha particles didn't come into contact with anything. But for those few that hit that dense nucleus, that caused this repulsion, this reflection of them coming backwards. And based on what we know now, Rutherford was correct. Most atoms are empty space. They have a huge volume, but most of it is an electron cloud where the electrons exist, and electrons are very tiny. So think of an egg in an empty stadium. That would be a volume of electron cloud. There's huge amount of space, but this tiny egg is moving around in this space. That's the difference. That's why a lot of these alpha particles were able to go through. So here's a depiction of, you can see there's a very tiny, now these are nowhere near drawn to scale, at all. So think of a huge stadium and all that empty space, and in the middle is maybe a ping pong ball, and that would be the nucleus that contains the protons and the neutrons. So if you see the blue lines pass through very easily because they didn't come into contact with anything. But there were a few, and the red ones indicated, that caused them to have an impact with that nucleus, and it changes the course of those alpha particles. So when you think of, it's hard to understand just how empty space is around the nucleus, but where the electrons exist is it's a huge volume of space for these electrons to move around in. So here's the volume of a nucleus is compared to the volume of an atom, has been compared to the size of an insect inside a football stadium. So what they're saying is, let's say this is a mosquito. That mosquito exists here in the center, and that would be the size of the nucleus compared to the empty, compared to the stadium and the parking lot where the electrons live. So there's a lot of volume. However, in the center, it's very, very tiny compared to what the electrons can live in. So the atoms are mostly empty space. And what we call this is an electron cloud. This blue is the electron cloud where the electrons exist. Okay, so now let's take a look at giving you more, see, I put it here, electron, the space around nucleus. So when we're discussing the charge, so mass and proton, I'm just going to jump ahead. Protons have a plus charge, neutrons have a 0, which is neutral, or you'll see this as just a line, and electrons have a negative charge. Now, when we talk about mass, atomic mass, you can see that a proton is equivalent to almost 1. It's got a few zeros after it. Neutrons, so these are almost identical. The mass is almost at 1 point, at a mass of 1 AMU, and electrons are very, very tiny. There's so many zeros in front that they're almost, weightless compared to the proton neutron. So when we look at the mass of an element, we pay attention to the mass with the protons and the neutrons, and we don't include the electrons because we would need so many more sig figs in order to include them in. So we look at the mass of the proton and we look at the mass of the neutron for the mass of whatever element it is that we're looking at. So here, if we look at this one here, we have 2 protons and two neutrons. This means that we're looking at helium. Helium has an atomic number of 2, which represents the protons, and it has an atomic mass of 4, which matches all of these added together. So this is how we can understand what element we're looking at, even if we don't know what the element is. If we have enough information here, we could look at the mass, and we could look up on the periodic table, and we also have the atomic number. So this tells me that 4 minus 2, is that right? 2 minus 4, I'm getting confused. We subtract 2 from 4, tells me that I had 2 protons, because this is atomic number of protons, and has 2 neutrons, which makes up the 4 for the mass. So again, this is a helium atom. This is what we're showing here. It's a neutral because we also have 2 electrons. It contains 4 particles inside the nucleus. 2 electrons are on the outside in the electron cloud. And this is neutral because the number of protons and the number of electrons